Assalamu alaikum, dear students. Welcome to the lecture of the waves and oscillations. In this lecture, we will talk about the simple harmonic motions of a closely coiled spherical springs. And if the springs are oscillating in the one dimension, then we will call this a linear simple harmonic motions. And you are also I think that you will be familiar with the simple harmonic motion, the motion in which acceleration is directly proportional to acceleration. So we will take one by one example and prove that this presenting simple harmonic motions are not. The first is a very simple case, horizontal spring system. Consider that we have a spring and a block is attached with this. If we displace this block from its mean position to some other points and cover its displace it by distance delta x, so a force will act on this. F will be k into delta x, that is restoring force. Restoring force mean that this force will act on the block to come back to its original position. So F will be equal to minus k into delta x, and from Newton's second law we have F is equal to ma, which is equal to minus k into delta x. So if we equalize this equation, F is equal to minus k delta x and F is equal to ma, we get acceleration is equal to, if we try to find out the acceleration from this expression, and we will divide this mass on the other side, and we will left with a is equal to minus k over m into delta x. So this is some types of constant. If we compare this equation with general equation of the simple harmonic, acceleration is equal to minus omega square and x. So this is some like omega square, which is equal to k over m, and acceleration is directly proportional to displacement. So this is a definition of simple harmonic motion. It means our spring system is oscillating with the simple harmonic motion. Because the acceleration of the body is proportional to the negative displacement, the negative sign shows that its direction will be always directed toward the mean position, because it will always try to obtain its original position, which is at equilibrium where no force is acting. So if we want to find out the time period for this, so time period will be equal to 2 pi and under root displacement over acceleration. Displacement is delta x, and acceleration is equal to minus k over m into delta x. So acceleration is equal to k over m into delta x. So this delta x will be cancelled with delta x. So we will left with 2 pi under root m over k, where m is inertial factor and k is spring factor. This is time period for the spring block system. Now we suspend this spring system in the vertical direction. In this case, our spring system, we will hang this. Consider it that our spring is in the vertical position as shown, and we will displace it from its mean position like this. Again, we have similar displacement, which is delta x, and the spring force is k into delta x. So our restoring force will be equal to minus k into delta x, and if we use Newton's second law, F is equal to F is equal to ma, which is equal to minus k into delta x. So if we try to find out acceleration is equal to minus k over m into delta x, so acceleration will be equal to minus delta x. And note that we have ignored the gravity in the vertical case, because our spring is massless, so we have not taken into account the gravitational force in this case. If we compare this equation with the general equation of the simple harmonic motion, acceleration is minus omega square x, so this is omega square. And again, we can find the time period for this time period is equal to 2 pi displacement over the acceleration. Displacement is delta x and acceleration is k over m into delta x. So we will have an expression for time period is equal to 2 pi m over k. Now we have some special case. If k is not given, then how we can find the time period of spring block system if k constant is not given? Suspend the spring without masses. For example, we have first suspend this spring without masses. This is the equilibrium of the spring alone. Now suspend the mass on the spring. Now definitely we will attach a mass. It will displace this spring with the delta L, and some force will be act like in the previous case. Let the spring stretch by an amount delta L. At this situation, the body is in equilibrium as follows in figure 3.32.9. This like k into delta L, which is equal to mg. Now these two forces are in the balanced positions, so we can solve this further. K delta L is equal to mg, and we can find the spring constant k is equal to m over delta L into g, and we know that time period is equal to 2 pi m over k. We are first not given with the constant. Now we have expression for spring constant, which is equal to m. If we put this values of k here, so we will get 2 pi m into delta L over g. M will cancel with m, and time period is equal to 2 pi delta L over g. It means we can find the time period if we are not given with the spring constant, but we have a spring system. And the second case is if the mass of the spring is not negligible. In the first case, we have neglected the mass of the spring. If we take into account the mass of the spring, then we have expression time period equal to 2 pi m plus ms. Ms is capital M is the mass of the spring over 3 over k. We will later prove this. Then how this factor, additional factor, come in the expression of the time period, we will prove this in the law of conservation of energy for the spring simple harmonic oscillator. We will derive this expression, that how this is coming into spring mass is affecting the time period. But for the shortcut, we have to memorize this, that 2 pi m plus m over. And in another case, let the two spring we have two spring k1 and k2 are combined together to a single mass in parallel. When we have two springs are connected in parallel and both have constant k1, another is constant k2, when the body is displaced by amount delta x, the net force on acting on the massive system, if we show you, these are the two spring constant k1 and k2, and both are in parallel, which are attached with this one mass m. So the first force on the first spring is k1 into delta x, and the force on the second spring is k2 delta k2 into delta x. So the net force will be equal to F, which is equal to sum of the two force F1 plus F2, because both forces are acting in the parallel direction. So k into delta x will be equal to k1 into delta x plus k2 into delta x, because this is the force corresponding to force 1, and this is the expression for the force corresponding to 2 second spring. So if we, because the displacement along y axis in the same for both system, because both are parallel, so delta x will be cancelled with delta x on the both side of the equation. K will be equal to k1 plus k2. So we can find the time period for this spring in the parallel system, 2 pi over inertial and inertial over spring factor. In this case, we will be effective spring constant, and effective spring constant is equal to k1 plus k2 for this wholly parallel system. In the fourth case, if we have two spring system in the series, so in this case we can solve our expression for the effective spring constant. We have k1 and k2 both are connected in the series. In this case, if net force is acting F and total displacement is x, and displacement in this spring is x1 and displacement in the second spring is x2, so our next total displacement will be x, which will be equal to sum of x1 plus x2, because this is total displacement, which is x, and this x is combination of x1 plus x2 also. So our total force is F and the total displacement is x. So F will be equal to k into x, where k is effective spring constant. F1 is equal to k1 into x1 for the first spring, and F2 is equal to k2 into x2. So if we write expression, x total x, which is total x is equal to x1 plus x2. So x is equal to x1 plus f2. X we can find the values of x. X is equal to here f over k. So x will be equal to f over k, and x1 is equal to x1 is equal to x1 is equal to f over k1, because same force is acting, which is the vertical, f over k1 plus x2 f over k2. If because the same force appearing on the both side of equation, so f will be cancelled on the both sides. We can cancel this force, and we will have 1 over k effective will be equal to 1 over k1 plus 1 over k2. If we take the LCM, then the effective spring constant for the series system will be equal to k1 k2 and product of the k and sum of the k. So 2 pi is equal to inertial factor over spring factor. So we can find the spring effective spring constant if we are given with the 3 spring and or the 4 spring. Similarly, we can modify our expression if we increase springs 1 by 1. And this is the another case number 5. If we have 2 spring system and attached are in this configuration k1 and k2, and in this case our block is in the between. So some student here confused that whether this spring systems are connected in parallel or in series. So we will examine these situations from the force. So first, if we displace this blocks for example with the force F1, which will be K1 into X, so similarly the same force will act on this spring and it will displace F2 K2 into X. So net force on the spring will be equal to F is equal to K1, F will be equal to F1 plus F2, which is acting on this block. So displacement will be the same. If we displace this spring, if we compress this spring with the delta x, so this spring will be elongated with the displacement delta x. So the net displacement will be same in this spring and in this spring. So F will be equal to F1 plus F2. F is equal to K into X, which is the net displacement, K1 into X plus K2 into X. So we can cancel the expression for the X terms on the bearing on the both side of the equation. So K will be equal to K1 plus K2, which is the case for the parallel. So our this configuration is the system for the parallel. So here we can conclude that if a spring constant K is cut into equal length, then the spring constant of each length will becomes n time of K. If we shorten the spring, means if we cut a spring into n pieces, then spring constants of each piece will be increased by n time. On the other hand, if the length of spring is made n time, if we are increasing the length, means if we are connecting the spring in the series, it means we are increasing the length of the spring. So in this case our spring constant will be decreasing with n time. If we have joined the two pieces of this same length, so our effective spring constant will be K over 2. If we are connecting the 3 pieces in the series, so our effective spring constant will be K over 3. And similarly, if we are cutting the spring in 2 parts, for example, if we have the spring system and cut into 2 pieces, so spring constant for the each piece will be equal to 2 time of K. If we are cutting the same spring in the 3 pieces, the spring constant for the each piece will be 3 time of K. So we can summarize our expression with this expression. So I will stop at this point and we will continue with another example of simple harmonic motion in the next lecture.